In this video, we're going to take a look at another application of functions, and those are direct and inverse variation. And these are two different types of relationships between numbers that are based on multiplication and division. The first that we're going to look at is direct variation. So we'll either be told that numbers vary directly or that they form a direct variation. And what this means is that one number is a constant multiple of the other. When one variable changes, the other is going to change in proportion to that. So if y increases, x would also increase. If y decreases, x would also be decreasing. So this means that the quotient between y and x is always going to be constant. Whenever we're asked to write the direct variation equation, our equation is always going to be in the form y equals kx. K is called the constant of variation. Those of you that have some background with linear functions may recognize this as being similar to our slope-intercept form of y equals mx plus b. And it's true that k and m, the slope, sit in the same spot. So k is also going to represent the slope of this line. But for right now, we're just going to refer to it as the constant of variation. And the way that we obtain that is by taking a y value and dividing it by the corresponding x value. So here's a direct variation listed out in its three main forms. We have the equation, y equals 4 times x. We have the table where we can see that each y coordinate is 4 times the x coordinate. And then we have the graph where we can look at individual points. We have 0, 0, so 4 times 0 is 0, 1, 4, 4 times 1 is 4, and negative 1, negative 4, 4 times negative 1 is negative 4. All three of these go together to represent the same relationship. Another way that we can check to see if a table forms a direct variation is by adding a third column and checking that we have that constant k value, that y over x. So 4 over 1 is 4, 8 over 2 is 4, and 12 over 3 is 4, and that value matches up with what we had in our equation. So the first thing we're going to do is we're going to try graphing the direct variation. Now again, those of you that are familiar with the idea of slope and y-intercept can use that. Since we haven't covered that yet, we're just going to do this with a table of values. So same as we've graphed other function rules before, we can type this into the calculator and get that table generated for us, but in this case this isn't really one that's super complicated, so we can just go ahead and come up with values ourselves. Remember, we usually want to have 5 values that we plug into the table so that we can see in the graph so that we can get a full complete picture. So if x is negative 2, x times negative 2 in this case would be negative 4. So we have the point negative 2, negative 4. If we pick an x value of negative 1 times 2, that gives us negative 2. So we have negative 1, negative 2. 0 multiplied by 2 will give us 0. Then we can keep going here. We can try 1, which will give us 2. And 2, which will give us 4. So if we look at this, all my points are collinear. They all sit together in one. Wow, that's really bad. We're going to try again. They all sit together in one straight line, and that line passes through the origin. Anytime we talk about a direct variation, it will always pass through the origin. And that's really important because that's one of the main ways that we can tell whether a linear graph is a direct variation. We can see whether or not it passes through the origin. That's because anytime I plug 0 into that y equals kx, I'm always going to get 0 back as my answer. So if x is 0, y is also always going to be 0. The second type of variation that we're going to talk about is what we call inverse variation. Now, in direct variation, as one quantity increased, the other did. In this case, when we talk about inverse variation, when one quantity increases, the other quantity is going to decrease. So they move in opposite directions. This results in a constant product. So whereas in the past we had k equal to y over x, in this case, because we have that constant leveling out, that increase that goes with the decrease, we're going to have a constant product. So our k values here is going to be equal to xy. We have two forms of the equation for an inverse variation, and if you're asked to give the equation, either one of these will work. Instead of y equals k times x, now we have k divided by x, and we'll also take the equation xy equals k. So here's an example in all three forms of an inverse variation. We have our equation y equals 60 divided by x, And we have a table, and here we're going to check if k is equal to that constant product of x times y. So we would go ahead and add that in. 2 times 30 is 60, 3 times 20 is 60, and we get 60 all the way down. So we know that this is an inverse variation with a k value of 60. When we graph the inverse function, or the inverse variation, right away we can tell that this looks very different from our direct variation. This is not a linear function. We're always going to have two pieces of the graph, one part up here, one part down here, and those will switch sides. We could have something that looks like what I'm going to draw in purple here if we have a negative constant of variation. So you just want to be careful with that. And this will always be centered around the origin. It won't cross through the origin, because if I have an x value of 0, that results in an issue here because I can't divide by 0. But it'll be centered around the origin. So if this graph looks like it's shifted to the left or shifted to the right, that means that it's not a complete inverse variation. If we want to graph this one, we don't have an intercept and a slope that we can use because it's not linear, so instead we are going to use the table of values. If I wanted to use the graphing calculator to generate this, remember your calculator always graphs things in the format of y equals, so I would have to divide both sides by x in order to get the equation that I could put into the calculator. Also keep in mind that the inverse variation has two pieces to the graph, so we want to make sure that we plot enough points that we can see both parts of the graph. So if we start with -2, we know that y must be -4, and we can plot that point, -2, -4. If we try -1, we know that that has to then be -8. So we have -1, and we go down 4, 8, and we can do one more, so we can do -4, and that gives us a y value of -2. So we've got this, we know it's going to come up something like this. We can go ahead and connect those dots. And we're going to put arrows on the end to show that that keeps going out in that direction. We also want to show the positive part, so we can have the point 1, 8, we could have 2, 4, we could have 4, 2. So we can graph all those points and get an idea of what this looks like. So we've got 1, 8 there, 2, 4 here, and 4, 2. And then we also know we have that one over here. And when we connect these dots, there's going to be a bit of a curve to it. It's kind of rounded, okay? It's not going to be pointy. We're not going to like draw straight lines between each. We're going to do a bit of a curve. And I know that's difficult. I don't always do the best job with it either. So just do the best that you can. All right, so typically what we'll be asked to do with this is to look at a relation and determine whether it is a direct or an inverse variation or neither. So not only which represent direct, but which represent inverse variation as well, and that would be our y equals k over x. So in this case, I'm just going to check y over x first, and -18 over -3 is 6, -12 over -2 is 6, -6 over -1 is 6. We skip 0 over 0 because we know that's part of any direct variation, and we can't divide 0 by itself. 6 over 1 is 6, and 12 over 2 is 6. So this is a direct variation, and our equation would be y equals 6x. Go ahead and pause the video and see if you can find any other direct variations. Just realized I didn't give you quite enough room there in all those tables. Alright, so if we look at these, for table B, if we start with our y over x, -20 over -4 is 5. That looks great. -10 over -2 is also 5. I'm doing all right. Then we get down to here where an input of 0 does not give an output of 0. So right away I know this doesn't cross through the origin, so it can't be a direct variation. And that's where I can stop. Moving on to C, we do the same thing, y over x. Each time we get 15, so that means this is a direct variation with the equation y equals 15x. If we look at D, we start with y over x. The first time we get about 16 thousandths, so a little bit of rounding there. The next time we get 1.6, so right away I know that this is not a direct variation. Now pause the video and see if any of the remaining two are inverse variations. Alright, so remember for the inverse variation we're looking for that constant product. So we check -4 times -20 is 80, -2 times -10 is 20, so those are not the same, so that cannot be an inverse variation. We move on to the next table, again looking for that constant product of y times x, and every single time we get 40, So that means this is an inverse variation, and we can write that as either y equals 40 over x or xy equals 40. Lastly, we have two different types of application questions that we might see. They may be as simple as just stripped down numbers, where if we have two that are in this variation, find a missing number if we're given a third piece of information, or we may have a little bit of context attached to it. The key phrase that you're going to want to look for anytime you tackle one of these questions is the phrase that either says varies directly or varies inversely. That's going to clue you in as to what represents y and what represents x. We will always start with y varying directly or inversely with x. So this one, it just says y and x. Down here, we say time it takes to fly varies inversely as speed. So that means the time must be y and x must be speed. It will always follow that same pattern. Y will always vary with x. Then if we look at the first example, oftentimes we're going to be asked to write the equation, so the first thing we want to do is find k. We know that y varies directly, so that means that k is going to be equal to y over x. So now I need to figure out two numbers that go together, and we have that here by them saying if y equals -4 when x equals 2. So this is an ordered pair in this variation, 2, -4. We're looking for the y value that goes with -6, so we can't use this yet. So k is going to be equal to -4 over 2, which is -2. So this means that my equation is going to be y equals -2x. Now I can use this to find the missing y value given that x equals -6. So I can say, okay, y equals -2 times -6, which must be 12. So my answer here would be 12. We can use the same idea and the same setup even if it's a word problem. We identify what x and y is, as we've already done. We figure out which two numbers go together, and they're usually going to be right next to each other. And we can find our equation and solve for the missing number. Go ahead and pause the video and see if you can answer the second question. Alright, so we've already identified that this is an inverse variation. So our k value, our constant, is going to be equal to x times y. So that's 900 times 6, and we get 5,400. So our equation can be either y equals 5,400 divided by x, or xy equals 5,400. Now we take the third number that we're given, that 800 kilometers per hour, and since that's a speed, that's an x value. So we substitute that into our equation for x, and in this case I used the second version because it's going to be a little quicker to solve for x, or for y. We can also use the other one, it doesn't matter. We could say y equals 5,400 over 800. We'll get the same answer of 6.75, and we're going to want to make sure that we include units with our answer here. So we would have 6.75 hours.